Now you know what a capacitor is and how does it charge. In this video, you are going to learn how a capacitor discharges, what is the relation between its charge and its voltage, and what do we mean by the capacitance of the capacitor.
After studying the charging process of a capacitor, now we are going to study the discharging process. That means the process in which the capacitor releases its stored electrical energy. In this animation, I have a circuit which is made up of a generator, an initially neutral capacitor, and a lamp. If I put the switch on this point, then the capacitor will undergo charging because it is initially neutral and it is connected across a battery. I have to increase the voltage of the generator to 1.5 volts. Now we can say that the capacitor is charged and the voltage of the capacitor is equal to 1.5 volts. Notice that the positive plate of the capacitor is connected to the positive pole of the battery and the negative plate of the capacitor is connected to the negative pole of the battery. In order to discharge this capacitor, we have to turn the switch into this point where the capacitor releases its energy through the lamp. When I put the switch in this position, then, as you will see now, the electrons will move from the negative plate to the positive plate through the lamp, and this will make the light bulb turn on. At the end of the discharging process, the voltage of the capacitor will be equal to 0. I am going to repeat it another time. I am going first to charge the capacitor. Then I'm going to turn it to this position, turn the switch to this position in order to discharge it again. I want from you now to look at the intensity of the current, which will be maximum at the beginning of the discharging and then it will reach 0 at the end of the discharging process. The number of the excess electrons or the excess protons on the plate of the capacitor is decreasing throughout the discharging process, and at the end of the discharging process, the voltage and the charge of the capacitor becomes 0. Now we are going to sum up the discharging process. As we've said that in the discharging process, the capacitor should be connected in series with the resistor or with any component that the capacitor will discharge its energy in. In this case, the switch should be connected to point 2. Note that the direction of the current in discharging is opposite to that in charging of the capacitor. Why? We have said in the previous animation that the positive pole of the generator is connected to the positive plate of the capacitor, and the negative pole of the generator is connected to the negative plate of the capacitor. In the charging process, the generator is the one which determines the direction of the current inside the circuit. The current moves from plus to minus. Then, in this case, the current will move from P, flow through or into A, and then to N. Whereas in the discharging process, the capacitor is the one which determines the direction of the current inside the circuit. Then it will move from the positive plate, goes out from A, and goes into B. Then, as we can see, that the direction of the current in charging and discharging process are opposite. In this table, we are going to sum up the voltage across the capacitor and the resistor and the current inside the circuit throughout the discharging process. First, the voltage across the terminals of the capacitor at any time is given by UC is equal to UAB. At the beginning of the discharging process, the capacitor is fully charged, then its voltage is equal to E. At the end of the charging of the discharging process, the voltage of the capacitor is equal to 0. The voltage across the terminals of the resistor at the beginning of the charging is equal to E, and at the end of the discharging is equal to 0. These are known using the law of uniqueness of voltage in parallel connections because in this case the capacitor and the resistor are connected in parallel. The intensity of the current in the circuit is calculated using Ohm's law. I is equal to UR divided by R. At the beginning of the discharging, I has its maximum value, which is equal to E over R, whereas at the end of the discharging, the current is equal to 0 because UR is equal to 0. In order to find the relation between the voltage and the charge across a capacitor, we are going to perform the following experiment using this animation. An initially neutral capacitor is connected across the terminals of a generator. We know that this capacitor is neutral because there are no charges accumulating on the plates of the capacitor. This button here tells us what is the quantity of charge or the charge of the top plate of the capacitor. Because the capacitor is initially neutral, then its charge is equal to 0 picocoulombs. In this experiment, I am going to vary or change the values of the voltage, and then we are going to record the corresponding value of the charge accumulating on the capacitor. In order to measure the voltage, I am going to add a voltmeter here, then connect it across the capacitor. The first value of the voltage is 0.3. The value here is negative because I have switched the wires or the connections of the voltmeter. Now the value is positive. So the voltage across the capacitor in this case, which is equal to the voltage of the generator, is equal to 0.3. What is the corresponding value of the charge? It is equal to 0.09 picocoulombs. I'm going to increase it a little bit until it reaches 0.6 volts. And now the corresponding charge is equal to 0.18 picocoulombs. If I increase it also 0.3 volts till it reaches 0.9 volts, then the corresponding charge is 0.29 picocoulombs. We've recorded these values in the following table. So, this table records the numbers or the values that were given in the previous experiment. The first voltage that we have chosen is 0.3. The corresponding charge was 0.09 times 10 to the power minus 12 coulombs, or 0.09 picocoulombs. If now we divide Q by UC, it gives this number, which is 0.3 times 10 to the power minus 12. The same calculation is done for the other two values of the voltage, which are 0.6 and 0.9. Notice here that if I divide Q by UC for all the values of Q and V, it gives me the same number, which is 0.3 times 10 to the power minus 12. Then Q divided by UC gives a constant number for one capacitor. What does this number stands for? This number defines a characteristic of the capacitor, which is called the capacitance of the capacitor or the capacity of the capacitor. The quantity of charge of the armature A is proportional to the voltage UAB across the terminals of the capacitor. Then QA divided by UAB is equal to a constant number, which is always positive. This constant defines a characteristic of the capacitor, which is called the capacitance, and it is denoted by big C. If we cross multiply the previous relation, then we will get QA is equal to C UAB. QB is equal to C UBA. The charge at the plate A is equal to the capacitance of the capacitor multiplied by the voltage or the potential difference AUAB. The charge on the plate B is equal to the capacitance multiplied by the potential difference or the voltage UBA. Notice if here I'm talking about QA, then I have to start with A for U. And if I'm talking about QB, I have to start with B for U. Remember that UAB is equal to minus UBA, then we will get QA is equal to minus QB. A capacitor charged under a voltage UAB has a quantity of charge Q defined as Q, which is equal to QA, is equal to CUAB. What is the definition or the meaning of a capacitor? Of a capacitance? The capacitance of a capacitor measures its ability to store electric charges on its armatures per unit voltage across its terminals. Not all the capacitors store the same amount of energy. The ability of storing energy differs from one capacitor to another. Then we have to define a characteristic which measures the ability of the capacitor to store electric charges. This characteristic is called the capacitance of a capacitor. The capacitance C is expressed in farad in the SI unit, but farad is a very big unit, so usually we use the sub-multiple divisions of this unit, which are 1 millifarad equal to 1 to the power minus 10 to the power minus 3 farad, 1 microfarad is equal to 10 to the power minus 6 farad, 1 nanofarad is equal to 10 to the power minus 9 farad, and 1 picofarad is equal to 10 to the power minus 12 farad. Let us solve the following application. Calculate the capacitance of the capacitor whose charge is 6 times 10 to the power minus 4 coulombs when the voltage across its terminals is 600 volts. Simply, I have to apply the charge-voltage relation such that C is equal to Q divided by U, and it is equal to 10 to the power minus 6 farads. Here, the units used are the SI units. Then, if I divide Q divided by U, it will give me also the SI unit of the capacitance, which is the farad. In this application, I have to find the electric charge which is carried by the armature A of a capacitor, where its capacitance is equal to 2 microfarad and the voltage UBA across its terminals A and B is 50 volts. QA, as we said before, should be equal to CUAB, but UAB is equal to minus UBA. Why did we use here UBA? Because in the given, UBA is given and not UAB. UBA in this case is positive and it is equal to 50 volts, which is substituted here. Pay attention that we have to convert from microfarad to farad, and that is by multiplying this unit by 10 to the power minus 6. The final number is equal to minus 10 to the power minus 4 coulombs.
I hope that you've understood all the objectives explained in this video. Don't forget to take notes when needed.